Okay, so hello. We had some problems with this computer, so we had to reinstall all the application. So now I have to adjust the parameters from scratch, but hopefully it works. So last time we ended somewhere after introducing information theory-based measure of distortion and information quantity. I'll skip to this part of presentation. Okay. This we have covered. Okay, somewhere around here. So what we want to do, we want to use the theory of random processes and statistics to quantify the effect of quantization. So what is the distortion that is introduced by quantization? And to find this, what I want to find is what is the variance of the signal in relation to variance of the quantization error. These two energy would be taken into a quotient, and the quotient would then measure what is the quality of the signal after quantization. This ratio of two energy is taken logarithm. If you take the logarithm of this quotient, and if the base 10, logarithm base 10, and if you multiply this quotient with 10, then we get this ratio in decibels. This decibels is commonly used measure, logarithmic measure of quality. Okay, and now first of all we have to find what is the value of this variance, signal variance as well as quantization error variance. We have to estimate these values. The quantization error is always within the one step size, and that is 1/2 of the quantization step plus or minus 1/2 of the quantization step. And we will assume that this random error, quantization error, is truly random, that it gets all the possible values in this range with equal probability. So we will assume that the error would have uniform distribution in the range of -1 step, half step size to plus 1/2 step size. And this probability density function, Fe of E, is then a uniform function that has the integral of 1, and it has non-zero value only from delta half to delta half. So this PDF, probability density function, Fe of E can be depicted in this way. So this here is error, E. This is the maximum negative error, which is minus delta half. Maximum positive error plus delta half. And of course, since this is the probability density, the integral must be equal to 1. In this case, if I know that the width is then delta, obviously the height must be 1 over delta in order to have the integral equal to unity. So this is a probability. Oops, sorry. Okay. Let me check if it is connected. Yeah, it's still connected. Hopefully it records. Okay. Density of the signal depends on the signal, on its statistical properties. And we don't know in advance about the signal and its probability. For the error, we can assume that PDF of the error is such as I depicted. It says here, oftenly we assume that the process of error has uniform probability in the interval plus minus 1/2 of the step size, with a density equal to 1 over delta in order to be probability density function. Such assumption is reasonable as long as we have a relatively large number of quantization levels. So this is not really valid if I have only maybe 2 or 3 quantization levels. So if the number of bits is 1, 2, so if the resolution is very low, then this assumption is not valid anymore. But if the number of quantization levels is large, let's say 256, we have 8-bit quantization, in this case, this assumption is more or less valid. So it is something that we can use. Okay, and then first of all, we can try to compute what is the expected value of error. Obviously, we know that the mean value should be 0 because if the error is symmetrically distributed, negative and positive, then the average error should be 0. So if I would compute some kind of sample average, I expect to get 0 mean value. But nevertheless, let's try to find the expected value of the error given the PDF that I depicted on the whiteboard according to the definition. So the expectation, as we said, can be found, so expectation of some random variable, E, can be found by multiplying E with its distribution, with its density, and integrating along all the values of this random variable E. So this is the definition of the expectation. If I want to find the expectation of some function of random variable, then I would simply insert this function here. For example, I want to find the expectation of E squared. Then I would simply write here E squared. And then use the same integral. I multiply then E squared with PDF of E, dE. In our case, since this PDF is trivial, it is constant value, this integral is then bounded with this non-zero interval range of the error, minus 1/2 of the step size up to 1/2. I can extract this constant value, 1 over delta, in front of the integral because it is a constant, and I get the trivial integral. I have to integrate E, dE in this range. And of course, we know that this integral is E squared over 2. So what we get, so the expected value of this, expected value of E is then 1 over delta, integral minus delta half to delta half, E dE. And that is 1 over delta, so it is E squared over 2 in the range minus delta half to plus delta half. And of course, what I should get is 0. Why? Because the upper bound gives the same value as the lower bound. The sign is cancelled in the squared value. So I get this delta squared over whatever, 8, I guess, minus the same thing on the lower bound. Delta squared over 8. And that is 0, obviously 0. So nothing very intelligent. We simply showed that if I have this kind of symmetric distribution around 0, then if I compute analytically what is the expected value of this random variable, I should get 0 as expected. Okay. And that is one part that was needed in order to find the variance. This was this part here. So in order to find the variance of E, I had to know the expected value of E. Now I can find the variance, because this sigma E squared is equal to expected value of E minus expectation of E squared. And now we have shown that this here is 0. The expected value of error is 0, so we have unbiased error, we can say. The quantization error is unbiased. So it simplifies to expectation of E squared. And then, according to definition, this is simply integral of E squared Fe of E dE over E. And this E range is the same as before. It is simply minus 1/2 of the step size minus delta half to plus delta half. I can extract this 1 over delta in front of the integral, since it is a constant. And I get the integral of e squared dE. And of course, I know that this is e to the third power over 3, 1 over delta, e cubed over 3 in the range minus delta half to delta half plus delta half. But since this is an odd function, now this upper bound and lower bound will not cancel. They will add up together. Since we have the negative value and this negative sign is kept after the third power. And finally, what I get is the result shown here, delta squared over 12. How come delta squared? Because I have this delta in the numerator and it is to the third power. And I have delta in the denominator of the first power. So when they cancel out, I get delta squared over 12. So what I get is actually the measure, what is the variance of uniform random quantization error caused by quantizer with step size delta. So this step size uniquely defines the variance. Smaller the step size, smaller the variance. Okay. Now, I would like to find the variance of the signal, just in order to be able to compute what is the ratio of this signal variance relative to the quantization error variance. And as an example of signal, we can use for cosine signal. So to have some actual signal, let's say that we have discrete cosine signal as, sorry, this a half is the amplitude, because we said this dynamic range is a, so in order to have a linear operation, this cosine must be within plus minus a half. Okay, this is plus a half, and this is minus a half. Okay, and this is the dynamic range of the AD converter A. Why is this important? Because we will use this number of quantization steps. So if I have one quantization step, this quantization step is then simply A over n. So if I have n quantization levels, then one quantization step, delta, would be equal to total dynamic range divided by the number of quantization levels, A over n. Okay, so this amplitude A half is then multiplied with the cosine function, cosinus omega 0 n, okay? So I get some random phases for which I evaluate this cosine function. This here can be treated as some phase, phi n. And this phi n, it has also uniform distribution in the range of 0 to 2 pi. So as this index increases, is if for some real number, omega 0, for some real value, I would get a sequence of phases, and this sequence of phases would more or less cover the range from 0 to 2 pi uniformly. So I would have simply different, if I draw the histogram, maybe this histogram would be something like this. Approximately all phases would be equally probable in the range of 0 to 2 pi. But this is, of course, only the principal value of the phase. So the principal value means that as this n increases, almost immediately I will get out of the 2 pi range, And after that, I simply remove all the integer multiples of 2 pi to get the principal value of phase between 0 and 2 pi. Because the cosine, of course, he cannot recognize what is how many integer revolutions has this phase made in between. It only measures what is the fractional part of the phase from 0 to 2 pi. So if I would plot the phase as a linear function, so this phi n would be some kind of linearly increasing function. And the increase is how much? If this is n and this is n plus 1, then this increase is exactly omega 0. So the phase increment for each additional time step is defined by this frequency omega 0. So how much instantaneous phase is added in each time step. Okay? But of course, as I said, the only thing that the cosine sees is the principal value of this phase. And this is then wrapped in the range from 0 to 2 pi. It can also be from minus pi to pi, it doesn't matter. So any unique interval of the width 2 pi is this principal phase value. And of course, as soon as I get out of this 2 pi range, I don't know how many integer revolutions has already acquired or exhibited in this phase, because this value is 2 pi. Okay, this is 0. Okay, and now as I have this phase drawn, now the question is, what is the probability of each phase value, of each possible phase value? For example, I might draw some range here. What is the probability that phase would be in this bin, in this range? So I simply count how many times the instantaneous phase value, the principal value, was, for example, from this phi min to phi max. And based on this, I will get the histogram. But also, in the limit sense, as this range is reduced, the bin size reduces, then I get finally the probability density function. Because this PDF is nothing else but the histogram where the bin size is reduced to 0. So I get what is the probability density that the phase would get one given value. And we will also assume here that this phase is uniformly distributed between 0 and 2 pi, because it doesn't make much sense at this moment to suppose otherwise. We will later show on that there are examples where such trivial assumptions is not valid. Just to be figurative, let's say that we have a case of omega equal to p quarter. What would then the phase sequence be? The phase sequence phi n will be 0, p quarter, p half, 3p quarter, whatever, 4 pi, okay, 5p quarter, then 6p quarter or 3p half, 7p quarter, and 2 pi. And this 2 pi is exactly the same as 0. Okay, this is the same principal value. So how many distinct phase values I have? Only 8. I only have 8 distinct phase values, and they are repeating. So in that sense, our PDF function is not a uniform density, but actually it is a set of 8 Dirac functions, which are placed at phi equal to 0, to p quarter, p half, blah, 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 up to the last, that is 7p over 4. And the probability of each of this delta is 1 over 8. So this delta function is scaled by 1/8.
So if omega 0 was like p to 2, we would have like the phase would be like p
Only 4 distinct values.
Yeah, P2, P,
Yeah.
P2 and 2P. Yeah.
Yeah. So for this kind of irrational frequencies, we have a density function that is not uniform, but is composed of set of Diracs, and due to this periodicity, I have this kind of discrete probability. But if this frequency is some irrational number, for example, let's say it is the base of the natural logarithm e times, for example, okay, e over 3 times pi. So this number here, e over 3, is some kind of irrational number. And if I multiply with the integer, I will never get the periodicity. So it doesn't have any finite period. And for that reason, it will simply cover all possible phase values with equal probability. So only for these special cases, when this term here is a rational number, 1 over 4, then I get this periodic behavior and the PDF becomes discrete. But with this multiplicative value, this omega 0, is an irrational number times pi, then of course it is a normal uniform density for all phase values. Okay, so this is the first assumption that we will use, is this simplified case where we have this uniform distribution of all phases. So if I would draw this probability density function, this f phi of phi is then uniform density from 0 to 2 pi and 0 otherwise. Okay? And now what I have? I now have the function of a random variable. Not only a random variable, because the function is cosine phi over half. Okay, so the for example, the expected value of x is then integral of this a half cosine phi with phi n as a random variable. This phi n is this argument of cosine. As I denoted this phi n, this here, this is phi n. So I treat this as a random variable with distribution PDF, as I said, this one. So this is the PDF, this f phi of phi is a random variable. So I will simply write this phi and omit this n, because it doesn't matter. This n was only to create a sequence. But if I treat this as a random variable, so it doesn't have any meaning. And I have to multiply this with the density, f phi of phi. Then I have to integrate over all the values of phi. Okay? And of course, now I can extract the constants. I know that this is 1 over 2 pi. Why? Because the width is 2 pi, so the height must be 1 over 2 pi. I can then write this expected value is the integral now from 0 to 2 pi. The constant part, okay, the constants are a, sorry. The constants are a half times 1 over 2 pi. 1 over 2 pi, what is left inside is the integral from 0 to 2 pi cosine phi. This is 1, there phi. Okay? And we know that the integral of a cosine function over one period is 0. So the integral, the area above the under the positive half wave and the negative half wave is of course the same. So this area cancels with this area here. And we know that this integral is 0 if this is one period from 0 to 2 pi. Okay, that was trivial. So I understand that this expected value of the signal is 0, and we use that in advance because the cosine function is running around 0. It's oscillating around the 0 value, so the expected value would be 0. Now what is more interesting is to find what is the variance, and for the variance I have to take the squared value of this function, x of phi. Okay, so the variance sigma x squared is the expected value of x minus expected value of x squared. As we have shown, this is 0, so I only get expected value of x squared. And now I have to, according to definition, write what is this expected value. Immediately I can take this a squared over 4 in front of the integral, r squared over 4, and 1 over 2 pi for the density part. So that would be a squared over 4, and then 1 over 2 pi for the density part, and what I have, the integral from 0 to 2 pi of cosine squared of phi, the phi. Okay, that is here. A squared over 8 pi, okay, integral 0 to 2 pi, cosine squared. And this cosine squared can be written as 1 plus cosine of 2 phi over 2. Okay? And in this case, the integral of this first part is something that is non-zero, but the integral of the second part is 0, because now we have what is the total integral over 2 periods. Okay, we know that the integral of 1 period, 2 periods, integer number of periods is always 0. So the integral of the second part vanishes, and the only thing that is left is the integral of the first part. And this integral is simply upper bound minus lower bound times 1/2. Okay, and that is then pi. So what I get is pi, and this pi is cancelled out with this pi. Finally, I get r squared over 8. So the variance of a cosine signal with maximum amplitude a12 is equal to a squared over 8. So we got what we desired. We wanted to find what is the variance of the signal, and we got a squared over 8. Okay, this is something that also you will learn in the electrical engineering when you have a sine mains voltage. Before it was 220 volts, okay, and it is the effective value of the sinus signal, but the peak value was by square root higher than that. And this here is squared value of the effective value, or the squared value of the maximum value. And for that reason we have a squared over 8, because originally the maximum value was a squared, a over 2 squared, so that is a squared over 4, and now the effective value is by square of 2 lower than that, and for that reason I have to divide by addition 2. So I have this sigma x squared that is equal to the dynamic range a squared over 8. Okay, and now I can express this value, this a, either through number of quantization levels n, or the other way around through number of bits. Because we know that this a, dynamic range, is simply n quantization levels times delta, and this n quantization levels was 2 to the power of b, number of bits that I use, times delta. Okay? And now I can write, okay, sigma x squared is then 2 to the power of 2b, 2 to the power of 2b, times delta squared over 8. Okay, and now that I have both variances, the quantization error variance and the signal variance, I can finally take this ratio. And this ratio in logarithmic scale is expressed as signal to noise ratio. So signal to noise ratio. It is measured in decibels, and it is defined as SNR 10 times logarithm base 10 of this ratio sigma x squared over sigma e squared. To emphasize the fact that this is the error due to quantization, then we will also write here signal to quantization noise ratio, SQNR. Signal to quantization noise ratio. So signal to quantization. Quantization noise ratio. Okay, SQNR. And now I will insert these derived values that we have found. So this is 10 log 10. This here is 2 to the power of 2b delta squared over 8. So that is the sigma x squared. And the sigma e squared was delta squared over 12. Now these two can be cancelled. And what I get is 12 over 8 or 3 over 2. 3 over 2. 3 over 2 for this part, and finally 2 to the power of 2b. Okay? Sorry. This can be simplified. SQNR is then, I can take only this part, 10 log 10 of 3 half. Okay, and then I have the second part plus 10 log 10 of something. But I will extract this 2b, the exponent in front of the logarithm. So I would have 20b times logarithm base 10 of 2. Okay? So the second part is then plus 20b times logarithm base 10 of 2. Okay? 20b logarithm base 10 of 2 plus this constant value 10 log 10 of 3 over 2. Okay? And this value here, this 20 times logarithm base 10 of 2, has the approximate value of 6.02 decibels, dBs. So what I get is this 6.02 times number of bits, b, and plus this constant offset term. This here is 1.76 dB. So plus 1.76 dB. Okay? Well, I have a simple linear function with some offset. Okay? I can draw this linear function. So if I would plot this SQNR, a number of bits here, so for b equal to 0, I get this offset value of 1.76. And then I have a linear function with the slope equal to, if this is b equal to 0, this is b equal to 1. So this vertical difference is 6.02 decibels. So the quality improves by 6 decibels for each additional bit that we add to the quantizer. Okay? That is the meaning of this expression. So this S squared R of B represents the logarithmic relationship between the signal level and the quantization noise level. And we see here that it has a linear relationship, and this expression shows that the quantization error is reduced by 6 dBs for each additional bit that we add to the quantization, to the AD quantizer. Okay? And this offset, this value of 1.76, it depends on the signal. So this function of a signal. And it's PDF. So for some signals, it would have higher offset, meaning higher quality for the same number of bits. For other signals, you would have lower offset, lower quality for the same resolution. And for our case of sinusoidal or cosine signal, we see that this offset value is 1.76. Okay, going further. Now we want to explore what happens with other kinds of signals that are more peak-like. Okay, the cosine signal has a nice relationship between the effective value and the peak value. So if I draw it once more, so if I have a sine or cosine, I know that this effective value of this cosine, and it is nothing else but the square root of sigma x squared. So if I take this variance, take the square root of variance, I get this effective value. And this effective value is how much? It is 1 over square root of 2 times a. In our case, a half, because our amplitude is a half. So our amplitude is a half. Okay? And this effective value is then 1 over square root of 2 times the maximum value a half. But if we have another class of signals, for example, of this form, okay, so this peak value is very high, so this A max, and the effective value might still be rather low, comparable to the sine signal, because this energy is concentrated in very narrow time intervals. So for that reason, we have low energy but high amplitude. And such signal is more problematic for quantization, as it will show. So to introduce this analytic relationship between this peakiness of the signal and its complexity in the sense of quantization, let's say that we know the crest factor of this signal. This crest factor is defined as a ratio between the maximum value, a half, and this here is effective value, square root of the variance. Variance is sigma x squared, square root of sigma x squared is sigma x, and it is the effective value of the signal. Okay? So this crest factor is nothing else but a half over this sigma x. So the square root of sigma x squared to this sigma x, okay? Effective value, okay? And now we know that the crest factor for the sine signal is square root of 2, because the maximum value is by square root of 2 higher than the effective value. But the crest factor of this green signal is much higher, because it has very large peaks and small effective value. Now, how will I take into account this crest factor? Simply by requiring that the dynamic range of the AD conversion must be adjusted to cover the complete range of the peaky signal. So from the plus a half times crest factor to the minus value. So this range of this green signal, this A max, plus minus A max, how much is this? So how much is this plus minus A max? It is simply crest factor multiplied with sigma x. Okay? Sigma x times crest factor and times 2 because I have positive and negative range. So the effective value, sigma x multiplied by the crest factor, positive branch, negative branch, I get the total range. So our AD converter must be adjusted with the dynamic range A in order to cover the whole range of this green signal, from the maximum positive value to the maximum negative value. Okay, so now we have this A, dynamic range of the AD conversion, is then this crest factor denoted with delta, or with delta. Okay, delta times sigma x, and times 2 because we have positive and negative side. Okay. Once we have this, now I can go the other way around, and I can express what is the step size for such a larger dynamic range. Because if I increase the dynamic range and keep the same resolution, of course I must increase the step size. So the step size is this total range, of course, divided by 2 to the power of b. Okay? Total range. A total range is how much? Total range is 2 times delta sigma x over 2 to the power of b. Okay? Now I will use this delta in the expression for sigma e, because we know that this sigma e has the simple expression delta squared over 12. And I will insert this delta for this sigma e squared. That is delta squared over 12. And if I write this inside, so it is 1/12 for delta squared sigma x squared over 2 to the 2b. 2 to the 2b, okay? And what is the sigma x squared? It is exactly this one. So the sigma x squared is supposed to be known. Okay, here. Sigma x squared is the numerator. So this is the variance of the signal. And this here is the variance of the quantization error that is now adjusted or dependent on the crest factor of the signal. Because depending on the crest factor, I have to increase the dynamic range to cover the whole range with number of quantization levels, that is 2 to the power of b. 2 to the power of b times delta. And if I simplify this as before, I get the same first part. This linear part is exactly as before, this 20b logarithm 10 of 2. Here it was also 20b logarithm 10 of 2. The only thing that changed is this second part, this constant part. Before, for the cosine signal, it was 10 log 10 of 3 over 2. And now what we get is 10 log 10, 3 over delta squared. So this offset part, SQNI offset, is 10 log 10, 3 over delta squared. And for our cosine signal, we can easily check that this is correct, because for the cosine signal, delta is equal to the square root of 2. Then we get exactly this 3 over 2 as we got before. But for some other signal that has higher crest factor, we get, of course, what? we get a larger value in the denominator. So this here is a smaller number, and means it is a negative logarithm. Okay, because for example, if this is 4, then this is 3 over 16. It is much less than 1. I get negative logarithm. So the offset is going down. I have the lower quality if I have higher crest factor. Okay? The resulting expression is identical for the cosine case if delta is equal to square root of 2. And obviously this delta is bounded from below with the minimum value of delta equal to 1. And it is for constant signal. If the signal is constant signal, then the maximum value is identical to the effective value. So the energy produced by the DC signal is equal to the peak value of this DC signal. Different from the sine signal, we have this square root of 2 between the maximum value and the effective value. So this delta cannot be smaller than 1. So this delta equal to 1 is the least possible value for this denominator. And as we increase this delta, then obviously this offset goes down and the quality goes down. Okay? The biggest problem for the quantizers are signals that have large peaks, but at the same time low energy. And that means high crest factor. Okay? Now I'm going over the time. So the idea is SQNR 0, SQNR offset, SQNR offset. It depends, it is a function of delta. It depends on crest factor. And it moves up or down. So higher quality means lower delta, higher quality, higher SQNR, and the other way around. So lower delta, higher quality, so higher delta, lower quality. Lower quality. Okay, we'll make a break now, and after the break we'll make a simulation to show you how it really sounds like when we quantize a signal. So what is the difference perceptually between unquantized signal and the one that is quantized with a given number of bits? 4 bits, 5 bits, blah, blah, blah. Just to see what is our perception of this quantitative measure. Because this quantitative measure is simple, that and that decibels, but how does it really feel? What is our perception of this error? And we will show this in demonstration during the break. I will prepare the demonstration. Okay. Okay. So first of all, I will tell you where you can find this example, because you will also use this example as a basis for laboratory exercises, for the first laboratory exercise, and you will modify it for the more complex task. So this is the simplest task. So I will illustrate, to be honest, not this example, but the example for the, I will show which one. So this example is the simplest one. If you go to the materials for the first cycle, this is not laboratory, but lectures. So you have these MATLAB demonstrations for lectures. You have here several zip files, and MATLAB code is for this inside this zip file. Example for the first lecture, example for the second lecture, and example for the fourth lecture. And these two are some audio examples. This example for the second lecture will be the basis for our laboratory exercise that we will modify to solve the problem that we will be having for the first task of the laboratory exercise. The example that I will show now is this example for the first lecture. I have already opened this example. It contains only one MATLAB source file, mt01 quantization.m, and the comments are in Croatian language, so we have to translate it in Google Translate, but I will explain it right now. So, first of all, this demo is for detailed plots, and we will first use this demo mode to show these detailed plots for one case, for one chosen number of bits for the quantizer, for one chosen resolution. This is the number of samples that will be drawn in this simulation. This is a simulated sampling frequency, 8 kilohertz, and this is a number of samples that will be synthesized to be reproduced on your audio output. And this is 1/2 of the sampling rate, so the idea is to have a short 1/2 second audio clip that will be presented. So I create the time index vector from 0 to n-1, but I will also create an interpolated index ni, and this one has a fractional step size on 1/16 to have this kind of continuous waveform representation of the discrete signal. I will simply evaluate the cosine signal 16 times on a denser grid than the original grid that is used for quantization. This is only for visualization of the continuous wave, okay, this Ni. And this is the amplitude or the dynamics of the conversion. A is equal to 1. Some expansion to have a bit wider region for the values shown in the plots. And now I have to select the frequency. I select a random number from 0 to 1 as this omega 0 frequency that defines the phase increment for each time sample. Okay? And now that I have this random frequency, I simply multiply this frequency with a sequence of integers, 0, 1, 2, 3, blah, 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 blah. So this n is a row vector with integers from 0 to capital N minus 1, caps N minus 1. And this sign is then multiplied with a12 because I want dynamic range to be A, so plus minus a12 is then dynamic range. The same is done for the continuous signal that is simply denser sampling of the same waveform. So instead of having integer sequence 0, 1, 2 for n, I have 16 times denser sequence 1 over 16, 2 over 16, blah, blah, up to 16 over 16, that is n equal to 1, and blah, and so on. So this is the same thing, but on a denser grid, just for visualization. Then if demo mode is active, I will select the number of bits here as 3. I will use a 3-bit quantizer, and that means 8 levels. 2 to the power of 3, 8 quantization levels. Okay? And now we enter the for loop, and this for loop goes for all resolution. In our case, it is only one resolution. B is equal to 3. First of all, it computes the step size. This caps D is the step size delta. So delta is simply A range, dynamic range, divided by 2 to the power of B number of levels. So in our example, if this B is equal to 3, then this is simply A divided by 8. So the step size is 1/8 of dynamic range. And in this operation, I simulate the operation of quantization. How I do it? I simply divide the value of the signal with the step size. I take the nearest integer value, and after that I multiply this integer value with the step size to get the quantized value of the signal. So this YQ is the quantized representation of the signal Y. And once I have this quantized signal, I can compute the error. The error is simply original signal Y minus quantized signal. And to find the expected value of variance, I will use here what? simple sample mean of squared error, sample mean of squared signal value to estimate the variance of the signal and to estimate the variance of the quantization error. So simply by taking mean value of sequence of squared errors or mean value of sequence of signal values, I will get the average squared signal and average squared quantization error. And these two values are actually estimates of the proper expectations that can be derived only from analytical expression based on the integrals. So this here is an approximation of the variance, signal variance, EY, approximation of the quantization error variance, ER. And once I have these two energies, I simply take the ratio signal energy over quantization energy, 10 log 10. I get the SNR. And this SNR is then plotted later on for all the resolutions. We will also have visualization, but to explain the visualization, it is the easiest that I start the program. So I will first start the program and explain how it goes. Figure 1 shows the continuous signal, and this is the one that is 60 times denser sampled, so like continuous wave. And green are samples, values of samples on the integer positions of time index. So for example, this is for n equal to 0, for n equal to 1, for n 2, 3, 4, 5, 6, blah, blah, blah. The frequency is some randomly chosen number, and this number is also printed here. So this omega, current omega, is 0.75. So the phase increment is 0.755 radians for each time step. Okay, so it is a randomly chosen frequency. So I see the samples. The green are samples. And what is plotted on the next graph, figure 2, is a histogram of the quantization error. And I have expected this to be uniform, to have equal probability of all errors from -1/2 of the step size to +1/2 of the step size. And I see that this is not exactly uniform, but let's say almost uniform. It will depend on the chosen frequency of the signal, this uniformity or not uniformity. Okay? On the next plot, I have this illustration of reconstruction. So how it goes. The dark blue line is still the original sine wave. The green dots are the original samples, unquantized samples. But with this horizontal light green line, I show the quantized value of the signal. So for example, I don't have this value as a quantized value. The closest quantized value is this one. So for the whole range here, I will take the closest quantized value to represent the blue line in this time region, in this time span. Then after this point, I will, instead of taking the proper value of the sample, take a bit lower value because this is a available quantization level for this value, the closest. It is quite close, but not exactly the same as original. So I will take this value to be quantized representation of this sample. Then for this value here, I take again another closest value, this value to represent this proper value of the signal, and I repeat it for all the samples. And in the next graph, I will add the reconstruction based on this sinc function, or approximation of sinc function. So instead of having constant value, instead of keeping this value as a constant step, I can interpolate sinc function through each of these quantized values, to this value, to this value, to this value. So instead of having constant value, I will interpolate this ideal interpolation function, sinc function. Okay, I will plot this interpolated version. So it is this red curve. So this red curve is better representation of the blue curve than this light green, this stepwise function. So this, it is called a zero order fold. So I take the value and hold this value to whole period. The first order fold will be like linear interpolation between two values. This value, that value, that value. So you get like a linear function between samples. And this red interpolation is based on this sinc function. And it is even better interpolation than simple linear interpolation. It is closer to the original. But the problem is that the values that are being interpolated are not the original values of the signal, because this red curve passes through this value and not through this value. So it passes through the quantized value and not through the original value. For example, here on the top, so this edge here is the point that this red curve must pass through, this quantized value of the signal. And the proper value is a bit higher. So the reconstruction is based on the quantized value of the signal, while the original signal blue was of different value. And that is the reason that this red curve cannot be exactly equal to the blue curve. And this deviation becomes larger, greater the distance between the light green curve and the actual samples that are shown with the dark green dots. Okay. And what you hear on the loudspeaker is the audio representation of the original signal first, and after that of this red signal. If I reproduce this red signal, it will be played on the speaker. So now I will make another example. Original signal and quantized version, this red one. The second one that is reproduced is this red quantized signal. And original signal, this blue, is the first one that is reproduced. And now I repeat this for several more examples. So definitely you can hear the difference between the original and the quantized version. You hear some distortion, it is audible.
It gets lighter.
Yeah,
like
yeah.
When you progress.
So,
that has to do with the frequency.
No, it's a random frequency. So it is a simple random frequency, but I guess that this error can be easier if the frequency of the original signal is lower.
Okay.
Then this random error has a higher spectrum range, wider spectrum range, and you can easily hear this higher frequency together with a low frequency signal.
So you spot the mistake, like
yeah. So maybe if you have here,
that's lower here.
so it is bzz, bzz, you hear this bzz.
That's lower.
Yeah. So if the signal is lower frequency, then you hear this bzz effect of this quantization error that is added to the original signal. And these are due to these random fluctuations. You have these sinusoidal fluctuations that are added to the signal, and these are high frequency fluctuations in comparison to the low frequency blue signal. And this is what you hear, this bzz, bzz, together with low frequency signal. Okay, and this is for only 3 bits of quantization. And that means I have only 8 levels. And you can actually count these discrete values. In this example, it should be 9. 1, 2, 3, 4, 5, 6, 7 here, 8, 9. I have one additional level because I have like a together maximum positive code that is 4 in this case, maximum negative code that is -4, and 0 code 0. So that is the reason that I have one additional code, not really 8, I have 9 levels here. One more. Okay? So I have only 9 discrete levels here for this example. Now I will increase the number of bits to, let's say, 5. I will terminate the program, Control C. Editor, okay. Now I will introduce number of bits equal to 5. And it is 32 levels. It is much harder to distinguish the original and the quantized version, so they are much more similar than with only 3 bits.
So as we increase the bits, to spot the difference, it gets difficult, more difficult.
Yeah.
Like if we put like 7 bits,
Yeah.
it would be more difficult to
Yeah.
distinguish the difference.
Because that is one kind of perceptual test that is performed for each of audio coders or speech coders, that they really reproduce this example. This is the original, this is the quantized, but you don't know which one is which. Simply, you have to say, are they the same or which one is worse? The first one is worse and the second is the worst.
Yeah, but you can't know which one is the worst.
Exactly.
Yeah.
So once you have a random error or random choice, then they know you cannot distinguish.
It is 50-50.
Yeah, if it is 50-50. So if the error is that you say that this is the original, this is the quantized, and you miss it in half cases, then obviously you are guessing, completely guessing what is the original and what is the quantized. And in this case, you say it's transparent. Nobody can really, with the certainty, recognize what is the original and what is the quantized version. So it's kind of blind testing. You don't know which is the original, which is the distorted version, and you have to simply judge which one is the better one. This one sounds better, or something like that. Okay, and this is really how they test this kind of audio coders or speech coders.
So they have a lot of samples and they keep hearing them.
So they have like a certified listeners. They have to be trained and they are even calibrated. They have some anchor recordings that they know should be, for example, scored with 3.5. And if somebody systematically scored this with 3.7, it will automatically downscale their scoring by this ratio, 3.7 to 3.5, in order to be comparable to other listeners and to other scoring guys. So they can really calibrate these subjective listeners in order to have the smallest possible difference in opinion between different listeners.
Can this be done with AI? Like, you know, I mean, instead of people hearing out put robots or some AI machine to spot the difference. To train it.
Like. They even tried this concept long before the introduction of AI in a way that they wanted to create a program that would simulate the human behavior, the human scoring. And it was based on actual perceptual measurements, but so they had these pairs, original, they had these labels, scoring, and they were trying to create an algorithm that would mimic the closest possible human scoring, and it was based on different tricks, I would say. So they tried to model the way that a human perceives this sound, and they tried to quantify this in some more measurable way to integrate this into the algorithm, and in this way they don't have to do this perceptual testing because this is costly. You have to take about how many guys to do this listening testing. So it is costly, and it is much easier to have some objective function that simulates human response as close as possible.
And brings out their sound.
Okay. We can also show, for example, the case that we discussed before when the frequency is rational. So when you have the whole number of samples per period, for example, 8 samples per period. In this case, we only have 8 discrete space values. And for that reason, the error is not random. because the error occurs exactly at the same values of the signal. So we have discrete distribution of error. As well as we have discrete distribution of phase, everything is discrete. So I will show this example by simply taking the omega function as a not constant value, not random value, but as a constant value. So instead of having random value for omega, I will have, for example, 1/3 of a pi. Okay, I can comment this, but it doesn't matter because it will simply write over the value. So it will be always p/3. It is the same frequency, and now the distribution of error is this peak-like. Why? Because if I plot the graph, I have exactly periodic signal, periodic quantization signal, and the error is also periodic.
It is symmetric.
Yeah. So this error is here. This difference between the actual value and the quantized value is very close because we have chosen higher resolution, 5 bits.
So we have almost no error.
Almost no error.
Yeah.
In this case, we have almost no error, and you could not hear the difference because the synthesized signal is of exactly the same frequency as the original signal, maybe different amplitude only.
Yeah,
it's the same thing. Yeah. So obviously you can hear that the number of bits, a very modest number of bits, is sufficient to completely cover transparency. 5, 6, that's it. Yeah. And what is used in the high quality audio recording and reproduction is 16 bits. So not 5, 6, 7, but 16 bits are used to have this high quality audio reproduction. Nowadays, not only 16, 24. So they say 16 bits is not enough. 24 bits should be used to represent the amplitude value. But it is, of course, an overkill, as you see, because you cannot distinguish with 6 bits the original from the quantized version. And with 24, definitely, nobody can hear the difference.
So like a machine that has the best sound is like using the most bits.
Yeah.
Okay.
So the idea is because increasing the number of bits literally gives a high quality. So you get 6 dB quality for each bit you add. And as we saw, as we can hear, 5 bits times 6 dB per bit, it's around 30 dB. So this 30 dB is sufficiently close to our perception limit, that we cannot distinguish the original from the quantized version. But there are maybe only a few people in the world that can really hear the difference. I can hear the difference, of course. It is maybe easier to hear the difference with the headphones, and especially if you reproduce different sound on your left and the right ear. Due to this spatial way that we treat these two signals as a spatial information, as a direction where the signal comes from, if you modify slightly left or right signal, you can hear this difference. It's like kind of false spatial information. You hear something, oh, the signal is not here, it is here, something like that. And that is the reason how they can really maybe hear a difference that otherwise with this reproduction cannot be heard. Okay? With normal loudspeakers in the room, you cannot hear the difference. But if you have headphones and reproduce one signal to the left ear, another signal to the right ear, maybe you can easier hear the difference between the two signals. Okay. Okay. And finally, we can also change in a loop the value of bits to quantize this signal. And this is done by converting this demo to 0. In this case, the quantization will be repeated from 1 bit, and that means actually 3 levels. Minus 1, 0, 1. Not really 2 levels, but 3 levels. Always plus 1. I will take always plus 1 level to have this symmetric distribution of levels. Up to 16 bits, and that means really 32,000 levels negative, 32,000 positive values. Okay? So I will repeat the quantization for all of this number of bits for quantization. and I will not reproduce the sound, but I'll only plot the curve. That is very interesting. For this case, for the special case that we have, when we have this rational frequency, pi over 3, then these blue dots are not behaving nicely, because these blue dots should be exactly along the green line.
But they're not.
Nowadays we have this discrepancy between the actual model that it expects uniform distribution of the error and what is not true. In this case, this assumption on uniform distribution of error is invalid. It's validated.
So this is not used.
No, I will show you if I have the random error, I should have started with that. If I have the random frequency, not pi over 3, but if I have a random frequency, in this case it will follow the model. Okay, I randomly select the frequency and I do the quantization with all the resolutions. Now the blue dots are almost exactly on the line. So the green line, is the one shown here. So this one, there. This one, okay? So this SNR offset and plus linear function 6 dB per bit. So this is this green line. And the blue dots are those that are derived from the selected number of bits, 1, 2, 3, blah, 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 and computed SNR. So I have computed what is the ratio of the signal energy relative to the error energy. 10 log 10 of that ratio, and I get the dB for one example. Okay? And I can see that this empirical SNR follow closely the theoretical function. So this green line is this theoretical function that we have derived from the PDF by assuming it is sinusoidal signal. Okay? And this green line is computed in the code at the end. So the expected SNR is simply 20 times number of bits times logarithm 10 of 2 and minus 10 log 10 of 2 over 3. So this is this offset term, and this is the linear term. Okay, linear term. And we see that for the trivial case, when the frequency is random, the empirical SNR follows closely the theoretically derived SNR. But when you have these special cases, when the frequency is rational, so for example, pi over 3, or whatever, let's say, pi over 8, for example, pi over 8, then this model becomes violated, and the actual behavior of the system is different from the expected behavior. Control C. Sorry. So you have some variations, some crazy behavior due to the fact that they have non-uniform probability of the error. Okay, error is has some kind of Dirac-like functions in the PDF. Okay, so this is the example. You can download the example from the web and you can play with it on your computer with MATLAB. Now I will continue with the presentation. Okay, so we have covered this here, and here it is a description of the code. It also has calculation comments, so please translate it to English. Okay, but you will understand. Okay, original signal, quantized signal with b equal to 4, so in this case 16 levels. If you count them, there are 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So 1 plus 17 levels. And so the error, quantization error, is this difference. the original value and the quantized value. So this difference, or this difference, or this difference. So this is the quantization error. And after reconstruction, if using this sinc function for reconstruction, I have this red curve. It is approximately equal to the blue one, but I have some kind of fluctuations that we can hear. Okay, this is a histogram of the error. It is almost uniform. Another example, blah, blah, blah. It is for 8 bits. Of course, it is almost identical. With 8 bits, you don't see the difference, you don't hear the difference. The red signal is almost identical to the blue one. Okay? And the error is almost identically distributed uniformly to the whole range of plus minus delta half. And the behavior of the model and the empirical SNR are closely following each other. But nevertheless, you can still observe deviations at low bit rates. So the model deviates, or the empirical, let's say, SNR deviates from the model when the bit rate is low. For higher bit rates, it follows closely. Okay? So for that, in that sense, we can say that this linear model, linear SNR model, is a high rate model. It's a very good model when the rate is high. When the number of bits is at least, let's say, 4 bits or more. But for low rate, if the number of bits is less than 4, 3, 2, 1, then this high rate assumption is not valid anymore, and this model is not that close. But still, it is quite good, I would say. Okay? A discussion. So the model predicts SQNR extremely well. Histogram quantization error is closer to the assumed uniform if the number of bits is larger, but also it depends on the frequency. So if the frequency is rational, then this is violated. For higher resolution, the behavior of quantizers can be very accurately predicted, and this approximation is the basis for the theory that is called high rate quantization theory, that we will introduce in the next lecture after the break. So what we have learned, what is quantization, what is the uniform quantizer. It is also called linear PCM quantizer, linear PCM, and this PCM comes from pulse code modulation. Very old abbreviation. We have introduced quantization, step and resolution, and converter dynamics. Discussed bipolar quantizers and corresponding codes that are usually encoded with two's complement values. We have discussed AD conversion accuracy and measured this accuracy by measuring the variance of the quantization error relative to the variance of the signal, and that way we introduced this signal to quantization noise ratio as a quantitative measure of quality. But nevertheless, we see that it is a simplified measure, but it is not completely compliant to the way that humans hear the difference. So it is a rather simple mathematical expression. We can play with it easily and have some optimum, let's say, based on SNR, but nevertheless, it doesn't mean that really the human will say the same. So, and that is the reason why they have this perceptual PESC score, perceptual evaluation of, I don't know. It's like an objective measure, but based on simulating the human scoring. Okay? So they have a special algorithm that you can run on your quantized version of the signal in comparison, in comparison to the original, and it will get the score approximately the same as human listener who scored this output. Okay? And we will make a break now because we will have a short discussion after the break about the raw data rate of different media signals, and after that we will really start with the so just to get the illustration why this issue of data rate is important, we will illustrate what is the raw data rate for different kind of media signals. And now I have example here. Okay, let's say we have a one-dimensional signal, let's say speech, and this speech is sampled with 8 1,000 samples per second, 8 kilo samples. And if each sample is represented with 8-bit number, then we get 8 times 8,000, 64,000 bits per second, or 64 kilobits per second. So that is the raw data rate that is on the exit or the output of the AD converter. Another example, if we have an image, then we have spatial resolution, and this spatial resolution is a number of pixels per row per column. So I have this m by n matrix of basic pixel elements called pixels, okay, basic image elements. And of course, each pixel is represented with some value. If it is monochrome picture, then it is, let's say, 8-bit value for the gray level, from dark, completely black, 0, 0, 0, 0, up to the brightest white pixel, let's say FF, and the highest positive value, 255. So this 8-bit value is then multiplied with the resolution. With full HD resolution, then this product of number of columns, number of rows, is approximately 2 million pixels. 2 megapixels is the resolution of full high definition TV, let's say. And then multiplied by, example, 8 bits, it is then 2 megabytes. So each monochrome full HD image would have 2 megabytes of data. And if this image is repeated with some frame rate, if it is a video sequence, then you also have to multiply this by frame rate. So then, for example, times 30 or times 60 or times 120 frames per second, it is again much higher required bit rate to quantize this monochrome image as a sequence of images. Then signal can be multi-channel, and the best example is video signal. So it is not monochromatic, but it has RGB or some different colors. Professor Grbić, Sonja will introduce different image coding algorithms and color spaces that are more effective for quantization than the RGB color space. But nevertheless, for example, if you have this RGB, it is three colors that must be represented for each pixels. 3 intensity. Intensity in red, intensity in green, intensity in blue. And then I have to multiply this, for example, here. Okay, this is a concrete example for full HD video signal. We have 3 colors, and the resolution for colors, for each of the colors, can be either 8 bits per color or even 10 bits per color. So the amplitude of red, green, and blue is represented as an 8-bit value or as a 10-bit value. If it is 8-bit value, then this resolution, spatial resolution, approximately 2 megapixel, multiplied with 8 times number of channels 3 times frame rate 60, and this gives a data rate of full HD signal. How much? Approximately 3 gigabits per second if it is 8 bits per color. If it is 10 bits per color, then it is 3.7 gigabits to transfer this sequence of 60 frames per second. It is transmitted over this HDMI connector, HDMI bus, and this HDMI bus, it has sufficient throughput to transfer these 3 gigabits or even 4 gigabits through the digital channels without any loss, without any compression. And nowadays it is even more challenging because we don't have only full HD resolution, we have this 4K or 8K resolution that is increased 4 times in X and Y direction, or even 8 times, so it is much higher resolution. And of course I would like to have as high as possible frame rate, ideally 120 frames, but not for this 4K or 8K because it costs quite a lot and it is infeasible. you can easily check the standards that are supported by current HDMI standard. If I go to Google, okay. HDMI, English. It is a connector of this kind, but if we go to the supported rates, it is a table somewhere around at the end of this description. Okay, versions. So the newest version is from year 2017. It is version 2.1 and 2.1a. The original version was the one that supported this 5 gigabits that was sufficient to transfer full HD with 60 frames per second progressive mode. But nowadays they are offering the total transfer rate of 48 gigabits in this new revision, 2.1 revision. And that is much higher, of course, almost 10 times higher than the original rate of the first HDMI standard. And why is so? In order to support these higher resolutions and higher frame rates. And this is how many bits you have per pixel, per color, 8 bits per color, so it is altogether 24 bits per pixel. But you could not use 16 bits per color for the original standard, for the HDMI 1.0, but it can be supported in this newest revision, okay? But also for the resolution. For the resolution, where do I have it? Who would know? Color depth, maximum data rate, blah, blah. That is the useful data rate is 42 gigabits. So the useful data rate is 42. The raw data rate on the line is 48, but the remaining, the difference is to encode the information without the clock. The clock is encoded in the data. So they don't have a special clock line, separate line, to transmit the clock and another line for data. The clock is embedded in the data line. And it is so-called different kinds of recordings are used to embed clock into the data. 8/10, blah, blah, something like that.
Yeah, but wouldn't it be better not to embed the clock in the program?
But in this case,
it is costlier.
Special line.
So you need more sources. Okay.
And so ideally, you would have signal line and clock line for each channel, for each of the channels. But then it is twice the number of lines. But nevertheless, each line is actually 2 lines because they are transmitted differentially.
Okay.
They are transmitted differentially as a twisted pair over the twisted pair. So for each of the data lanes, you should have additional clock lane. And it will multiply the number of required wires a lot. And for that reason, they embed the clock into the data. So
that's not practical, actually.
Yeah. It is explained at the beginning, so it is, of course, more technical stuff, implementational stuff than the theoretical stuff. So it is for electronic engineers to understand how this actually works. Okay? But just to understand, the rate is enormous. 48 gigabits, it is an enormous rate. There's practically nothing you can do at this rate except transmit data over this channel.
It is more than enough.
You know that even Ethernet cable is a complicated stuff with 10 gigabits. So if you have 10 gigabit switches, 10 gigabit infrastructure, it costs a lot. And this is 48 gigabits. It is only one direction, of course. The Ethernet cable is both directions, symmetrically. But also this has a larger number of lanes than the Ethernet cable. This one has only 4 twisted pairs. Okay. So the same channel is used to transmit the audio information as well, and everything is done through this kind of connector, standard connector A, or mini or micro connectors for HDMI. Okay, so very sophisticated standard, but as you go with higher rates, the cables must be shorter. So the maximum length of the cable is limited depending on the rate that you want to transfer. So but for the lowest rate, this 4 gigabits, you might have maybe 15 meters, no problem. But for the highest rate of 48 gigabits, the cable must be maybe 1 meter maximum. Otherwise, the signal is corrupted. Okay. So that is just to introduce the concept of rates and why these rates are important and why it would be nice to introduce some kind of compression, especially if that must be stored. It is not a problem for the last transmission from your computer, from your graphic card, to the display or to the projector. But of course, if you have to transmit this signal as a raw signal on the data lines of the internet, it would be impossible without compression. So we have to compress the signal a lot in order to be able to transmit it or to store it on your computer. And now we will skip to next presentation. No, save no. The downloads. Full screen. Now we'll go to the actual discussion of how to encode this stream, how to compress it. So most natural signal as well as various media signal show the property of statistical dependence of samples. And this statistical dependence of samples is a source for potential data compression. This data compression is a kind of coding that aims to reduce the number of bits to represent this information. So coding in general is any kind of representation of information by single bits, but as a special sub-branch of coding is data compression. Because the idea, if I have encoder that does this compression, then the output rate would be much lower than the input rate. This is then stored or transmitted over the network, and the decoder does the opposite, does the decompression, and gets the final output data of the same rate as the original rate. But of course, maybe not the same quality. So this encoding and decoding might be lossy. So they might introduce some error, and this error is such that typical user will not be able to distinguish the original and the decoded and decoded version. So the term coding is often used as a synonym for compression, which will be the case in our materials. But nevertheless, as a compression, as a narrower term, it is actually a process of removing redundancy. So redundancy removal. The task of compression is transfer of the media format of nominal accuracy, or this raw format, into equivalent form of digital representation, in which this redundancy is removed, or reduced at least. And then on the decoding side, to reconstruct the original signal as close as possible, but only through this original part, or this most important part of the signal. This intelligent, I would say, or informative part of the signal. And everything that can be predicted or somehow reconstructed without transferring the information is done by the decoder. So the decoder fills the gaps, I would say. So the intelligent part of the signal is reconstructed completely, and this predicted part of the signal is then reconstructed by the decoder from this informative part of the signal. Okay, so coding as a broader sense can be divided in 3 subcategories: source coding, entropy coding, and general coding. And we will be talking about the first 2, about the source coding and entropy coding. And this general coding is actually opposite of compression. It is adding additional redundancy bit in order to improve the transmission quality or the number of bits that are in error, to reduce the number of error bits. So I introduced like a redundancy just in order to be able to reconstruct the original information if the data channel corrupted the message. So if, for example, I have a random bit error in the transmission process, that each 100 bit is randomly toggled, then the idea is, can I add additional random redundancy bit in order to do the error correction, to restore the original data stream with corrected errors. So although I have this random bit error, I can still reconstruct the original message based on these redundancy bits. And that is this channel coding. And this is an essential part of any mobile transmission channel. So you cannot transmit data on a mobile channel without data corruption. You always have this data corruption. You always have to protect this data packet with additional redundancy part of the message in order to be able to reconstruct the original message with lower bit error than the one that is caused by the errors in transmission. Okay? But we will not be discussing this part. We will only be focusing on source coding and entropy coding. So the first two are used in the context of compression. And this compression can be done in two ways, as lossless coding and lossy coding. The best example of lossless coding would be zip. So you have a file and you run zip on your computer, and the file is smaller, but you can unzip it exactly the same as it was without any error. So it is lossless. You reduce the information, but nevertheless get the same information as you had before. So no difference between the original and reconstructed version. But with this zip, if you try to zip your JPEG file, for example, it will not shrink. It will practically remain the same size as the original. Maybe you will get 1–2% reduction of size after zipping JPEG, or after zipping, for example, MP3 file, audio file, the same thing. Because these files are almost random-like. They already have all the redundancy removed by the compression encoder, and zip can do nothing about later on, because it is practically uniformly distributed probability of all symbols. So if you count all values in this byte representation from 00 to FF, you will get equal probability for all codes. And there's nothing that zip can do to have some kind of additional reduction. But of course, zip standard is useful if you give text as an input. Then you will get quite high compression. Because why? Because you have very discrete probability of only the symbols that you use to represent individual letters in your text. So this ASCII code of A is whatever, 32 hexa, whatever, and it happens with that and that probability. And if it is often used letter, then this zip could use a shorter code to represent this often used letter, and a longer code for those that are occurring less often. Okay, and in that sense, it can achieve higher compression ratio, much higher. But we'll mainly be focusing on lossy coding, because with lossy coding, you can achieve much higher ratios of compression. For example, for audio coding, this ratio is around 20. So compared to the original WAV file that you start from, you would have this MP3 file, like I called it audio, that is 20 times shorter than the original file on a CD disk. Very much similar for the video encoding, even higher ratios of 20. No? Okay? So what is the difference between the source coding and entropy coding? The source coding is a kind of coding that takes into account what is the source of this signal. So, for example, if it is human voice, then it has quite characteristic properties. And these properties of human voice can be utilized to have the best possible coder with highest compression for this signal. But if you try to use the speech coder for audio, it will not work. So audio, in general, if you want to encode music or whatever, then simple speech coder is insufficient to encode, or it is not as effective as the audio coder or audio coder. So for audio signal or music, you have to use special coder that is suited exactly for audio signal. Okay, so this idea that a source defines the kind of coder that we are using is then the source of this attributes, so source coding. So we know what the source is, and the coding is based on the characteristical properties of that source. And on the other hand, entropy coding doesn't know anything about the source. It only sees numbers. Only the statistical properties of these numbers representing values of the signal is the only thing it sees. And first of all, we will study this entropy coder because they are the most simple one. So it attacks digital message without knowing its true source or the structure of the signal, and what it utilizes is only estimated statistical properties of this set of samples, of these numbers that are values of the samples, let's say. Okay, so we will now start with this part of entropy coder description with short introduction, what is the information and what is the entropy. In preparation of these slides, one colleague of mine, it was my doctoral student, contributed, and he is now professor in Basel in Switzerland. Very renowned, I would say. So you can Google him. You can also try to contact him to get maybe some grant to go to Switzerland. Okay, so what Ivan prepared is the following. So what is the information? Information is actually the amount or the level of surprise due to an event. Okay? That is the measure of information. If you are more surprised, then I transfer to you more information. If you're not at all surprised, then you are bored. I have told you nothing. So I have conveyed to you no information. But if you are very much surprised, then it is huge quantity of information that is conveyed to you. Okay? So it is a measure of surprise, level of surprise. For example, if you want to guess the woman's name, for example, someone tells you that the first letter of the name is M. And in Croatian language, this M is a very common female name, Maria, Maya, whatever. So there are many female names starting with M. And if you get only this information, it is a very big information because you don't know what is the actual name of the girl. It only starts with M, and there are many different names of girls starting with M. But for example, if the first letter of the name is Zh, and it is of course much seldom you use first letter, there may be only 2 or 3 names that start with Zh, Željka, Žana, whatever, and that's it. So much larger quantity of information is transmitted to you by telling you, okay, the first letter is Zh. And it's the same, this game, how it is called, I don't know, hanging or whatever, when you have this, guess the letters in whatever. You open letter, okay, open the letter, third letter, okay, it is S, okay, blah, blah, open letter S, okay. You have to guess what is the sentence by opening one letter after another, and then you have to guess the whole sentence. So that is the idea. So you have to first select those letters that are most informative, that you get the highest possible quantity of information by opening those letters. And of course, if you are not that lucky, you will open nothing. So if I say open the letter S, and there's no S in the sentence. So bad luck. Try another letter, and so on. So that is the idea how to illustrate the information. Okay, now let's say that we have a memory source of information and it generates discrete symbols. For example, let's throwing the dice. This dice has 6 sides and we have output symbols 1, 2, 3, up to 6. And in this case, this alphabet consists of 6 symbols, sides of the dice. And in that case, the probability, if it is unbiased dice, is the same for each of the 6 symbols. So whether it is 1, 2, up to 6. But nevertheless, the probability might be unequal or non-uniform. For example, if it's biased dice, you have put some kind of weight on the one side, and it always turns on that side, and in that case, you get different probabilities for each of the possible outcomes. Maybe number 1 is more probable than any other number, blah, blah, blah. So we have alphabet, we have the probability of each symbol from that alphabet that can be observed. So the probability of generating each symbol from this alphabet will be denoted with pi. So for example, if in the example with dice, number 1 turns out in half of the throws, then the probability of this symbol 1 would be 1/2. And for all the other symbols, 2, 3, 4, up to 6, the total probability will be another half. Okay, so for each of the symbols we have corresponding probability. And the amount of information due to observing each symbol would be then logarithm base 2, 1 over pi. For the same example of dice, if this symbol 1 occurs in 1/2 of the experiments, of the dice throws, then we have this 1 over 1/2, that is 2, logarithm base 2 of 2 is 1. So there is 1 bit information if number 1 fell on the dice. 1 bit information is conveyed to you. But if, for example, number 6 is observed on the dice, and the probability of this number 6 is not 1/2, but maybe 1 over 32, then in this case, this is logarithm base 2 of 32, and that is 5. So this is 5 bits that you get as information if number 6 is observed, because it is much rarer event than when 1 falls. Okay? And taking the logarithm base 2 gives the results in bits. But there is also alternative to using a logarithm, natural logarithm, logarithm base e, and then this measure is expressed in nuts. So logarithm 2 bits and logarithm natural e nuts, not a sub. Nuts. Crazy guy. Okay. And finally, if I know the information for one symbol from the alphabet, for example, for 1, as you said, 1 bit, for 6, 5 bits, okay? Then I want to have the average information of the source. To get the average information of the source, then I simply have to multiply this by the probability of that symbol. So I said, for symbol 1 that I got on the dice, it is 1 bit, but it happens half of the time. So 1 bit times 1/2. Then another plus for the second symbol, blah, blah, out of the 6th symbol, probability is 1 over 32 times 5 bits. Because I got 5 bits by observing number 6 on the dice. Okay? So I would compute what is the average rate, what is the average information rate generated by this source. How? By simply averaging this, but using the probability for each of the symbols, like a weighted average. So this value, logarithm 1 over pi, is averaged with the weight pi for the all symbols, for all the symbols in the alphabet. And this can be also rewritten if I take this pi into the numerator and extract -1 in front of the logarithm. I get the negative sum pi times logarithm pi. I don't express special logarithm base 2, but if you use logarithm base 2, it is in bits. If it is natural logarithm, then it is in these nuts. And this here is then the measure of information quantity of this source, and it is called entropy. So this H of S is a measure of informativeness of this source, and this, we call it the entropy of the source. So how informative is this source? Okay, so this H of S is a measure or amount of information generated by the source. Simply by averaging amount of information per symbol. So this is expression you should remember in the half of the night, in wake up, I know what entropy is. The entropy is the negative sum of pi times logarithm base 2 pi. Very important expression. Entropy, according to this definition, corresponds to the smallest possible average length of the encoded message in bits. That is very important. So, for example, if I would like to encode the message generated with this generator, with symbols S1, S2, up to Sn, with probabilities P1, P2, up to Pn, how to encode this message with the shortest possible average code length. The entropy is the lower bound for that. You cannot encode this message with a lower average rate per symbol than the entropy rate. The entropy rate is the lowest possible coding rate, average coding rate for the source given here. So for the source with n symbols with probabilities P1 to Pn, that is the lowest possible average coding rate to encode the information without any loss. So this is the smallest possible average length of the encoded message in bits. In doing so, we assume that the source is memoryless. That is very important. So we don't introduce any kind of conditional probability of the next symbol given the previous symbol. So we treat them as completely statistically independent. What happens in the step n plus 1 is completely independent of what happened in step n, in the previous step. So it is memoryless source, and for that kind of sources, the entropy is true measure of information. But if there is a kind of dependency between the samples, then the actual rate can be lower than the entropy, because this dependency can be utilized to achieve a higher compression than given by the entropy bound. So this entropy bound is really a bound, but for the memoryless case. And if you succeed to prove that you can encode the message with a lower rate, lower than this entropy rate, then you might get the Nobel Prize as a new information theory expert that proves something, let's say, new. But nevertheless, it's, I would say, impossible to prove something like that. But nevertheless, you can try. Maybe you can prove it and you can get a new Nobel Prize. And then we come to the variable length codes. And these variable length codes are one way how to achieve rates that are close to the entropy bound. They might be almost sometimes identical to the entropy bound, but nevertheless they are close, slightly above the entropy bound. So the one way how we can utilize this different probability of symbols for each of the symbols in the alphabet is to use the code that is proportional to the number of bits required to encode this symbol. So if I actually have a variable bit length encoding, variable length of the message, I would say for each symbol, maybe for those that are occurring very seldomly, like this 6, I would use a longer code. And for those that are occurring in almost each second row, like 1, I would use the shortest possible code. Only 1 bit to encode, it was 1. So I would use the shortest possible code for oftenly occurring symbols, and longer codes for those that are occurring less often, seldomly. And that is the idea of variable length codes. Shorter code words to more probable symbols and the other way around. But there is a problem, so how to construct the code to be, let's say, decodable. Because once we create this message, each symbol is of different length. So I write 3 bits for the first symbol. How do I know that this is the next symbol starting from here? Because if it is 8 bits, I know. I read 8 bits, that is one symbol. ASCII code, it is letter A. But if it is, for example, 3 bits, 1 bit, 5 bits, so each symbol is of different length, I don't know the boundaries. So how to find the boundaries of each letter in the sequence if each letter is of different width? So it is a tricky problem, and the solution was found by one guy, this guy here.
Can't we try our own boundaries, like to set the boundaries on our own? Or that's tricky?
The problem is that it depends on the source, but since you don't know the message.
Okay.
You don't know the message, and each letter that you use on the alphabet has a different length of the code.
Yeah.
So you must construct a code that uniquely defines the boundary between two symbols, neighboring symbols. That you know, okay, this was the first symbol, it was only 1 bit in length, and immediately after that it was another symbol, for example 6 with 5 bits. How do I know that it's another symbol? So the idea is, the answer to that question was found by this guy, Huffman, David Huffman. He lived in the last century, from 25 to 99. He was a mathematician, and as a hobby, he liked to fold the paper. So he created this kind of 3D surfaces from paper by folding it, and he was very famous for that, except for inventing Huffman codes. But Huffman codes, I will explain them on one particular example, because it is the easiest to illustrate them, and we will go there later on to the definition. Okay, so suppose that I have only 4 symbols, A, B, C, D, and they have non-equal probability. So this one has 1/8, 1/2, 1/4, 1/8. Okay, so the idea that this Huffman got, you have to construct a binary tree, like a binary tree. And to construct this binary tree, you first start with the 2 symbols that have the lowest possible probability. So you take this A and D, because they have probability of 1/8. And then you combine them. So A and D are combined into one branch, and now this branch has probability of 1/4. So for example, this is upper branch encoded with 0, lower branch encoded with 1. I will assign this to symbol A, I will assign 1 to symbol D.
It doesn't matter.
Doesn't matter.
Okay. It's just symbolic.
Just symbolic.
Okay.
And now I have like a compound branch that represents together symbol A and D as one symbol, let's say. And now I compare this AD together with C and B. Now this AD has probability 1/4, C has probability 1/4. Now these two are the 2 leaves with the lowest probability, and I have to combine these 2 leaves into one new branch. So I combine this compound branch for AD with the branch for C, again assigning 0 to this upper branch. It was just my choice to give 0 code to the upper branch and 1 to the lower branch. You can do it the other way around, it doesn't matter. And now I have this compound branch that is now with probability of 1/2. 1/4, 1/4, 1/2. And finally, I repeat the same procedure. Now I only have this B to be combined with this compound branch, and I finally come to the root of this tree. Again, assigning 0 to this upper branch and 1 to the lower branch of B. So what I got? I got coding table that tells me if I start from the root, if I want to encode letter B, I would go down. I would encode it with 1 bit symbol of length of the value 1. Okay? So I would encode the symbol B with 1 bit 1-bit wide code, okay, and this code is 1. If I want to encode C, letter C, then I have to go up and down, 0, 1. So I have this 0, 1 as a 2-bit length code to encode letter C. And finally, if I want to encode A or D, then it is up, up or down. So 0, 0, 0 or 0, 0, 1. Okay, 0, 0, 0 is A, 0, 0, 1 is D. But what we see here, that by constructing such a tree, we have got a prefix code. And that means that, for example, if B starts with 1, no other codes start with 1.
It's unique.
It's unique. Okay. So if the first bit of the symbol is 1, no other symbol should start with 1. Okay, in this case, okay, now this one started with 0, okay, and the next branching is here. If it is 1, it is C directly. If it is 0, it is either A or D. I have to read another bit to select whether it is A or D. But by constructing such a binary tree, we have constructed unique prefix codes. Unique prefix codes. It is then written here. So we store the symbols by probability. We choose 2 symbols of least probability and make a subtree of those 2 children. Okay, so we create a subtree based on 2 symbols with the lowest probability. After that, we assign the parent probability, that is the sum of these 2 probabilities of the children, and put it in the list of symbols and remove the children from the list. And then repeat the procedure until we have exhausted all the symbols from the dictionary. Okay, and in that sense we assign code words to each leaf of this tree by simply following the path from the root to each of the leaves. So by starting from the root, 0 or 1 or 0, 0, 0 for A, blah, blah, blah. So the only thing that I have to transmit to the decoder is the structure of this tree, this table here. So this table must be somehow transmitted to the decoder, such that when he observes the whole sequence of this, he knows how to interpret the sequence. For example, we'll show in this case, let's say that the original message was B, A, D, B, B, C, B, C. Why have I chosen exactly this message as an example? Because it exactly follows the probability of the symbols given in the table. So how many times have I observed B? I have observed B 4 times out of 8 letters. So it has a probability of 1/2. And that is what we designed to observe here. B should be probability 1/2. Then C should be 1/4. And that means I should have at least 2 C's. 2 C's in the message. I have it here, I have it here. Okay, 2 C's. And I have 1A and 1B because they have probability of 1/8. So now I have constructed one message that exactly follows the probabilities of symbols that I've given in the table. And then I construct the coded message. So B is encoded with 1. Okay, I write 1. So this light green is code for B. After that follows A, and A is 0, 0, 0. Okay, 0, 0, 0 is A. After that follows D. D is 0, 0, 1. 0, 0, 1. Okay? And how do I know that I have the boundary between 1 that is B and A that is 0, 0, 0? Because I know that if I read 1, this 1 is leaf. I know that I have come to the end. That is the symbol. I don't have to read any additional bits from the bit string. I have come to the end of the tree, and I simply write, this 1 is B. Then I start with a new symbol. And then I observe 0, 0, 0, what means go up, go up, go up. Only then I'm at the end of the tree, I'm at the leaf, this leaf is A. And you simply repeat this. And now I simply count how many bits I have in a sequence to encode the whole message. And I observe that it is 14 bits long. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the message is 14 bits long. If I would use binary code for 4 symbols, that means 2 bits per symbol, I have 8 symbols, it will be 16 bits. So I have gained how much? Only 2 bits. Okay, not that much, but it is less than 16. So I have some gain in compression. Instead of transmitting 16 bits, I can encode message with only 14 bits. And if I would divide this 14 with the number of symbols, 14 over 8, I would get the average rate per symbol. So how many bits per symbol in average do I have to encode this message? And this average code word length is then found how? Simply by taking the probability of the first symbol A, 1/8 times 3. 1/8 times 3 bits for A. This is this part. Then another 1/8 times 3 for D. Then 1/4 times 2 for C, because C is 2 bits. And finally, 1/2 times 1 bit for letter which one? B. That is half probability. And what I get is the average bit rate per symbol, 1.75. It is exactly the same as 14 divided by 8. I get exactly 1.75. And if I would compute the entropy, I would get again the same value. So the entropy computed with this expression, negative sum pi log 8 of pi, will give exactly 1.75. So it is like a fabricated example where the average code length constructed by the Huffman code would give the result that is equal to the bound, to the entropy bound. So I have the optimum performance of this encoder, or this entropy encoder, because it operates on the entropy bound. It cannot be better than that. So it is ideal. Okay? Now it is 7 o'clock, so we will make an end for this presentation today. And we will continue next week. Do you have any questions? Maybe